All right, rock and roll. We're going to talk about a new concept called Thevenin's equivalent. Now, this will not be on the take-home test I'm going to give you guys, and don't freak out or anything like that. Take-home test is not going to be that bad. We have trying times right now. Trying times require a little bit of adaptation in order to make sure that we finish off this semester and you guys get the information that you need in order to actually be successful in either Circuits 2 or if you get reference this information later on down the road in another class. Now, the cool thing about Thevenin's equivalent within Chapter 4 is that this is actually the first design technique that electrical engineers utilize in order to basically be able to make changes within the system without having to do a lot of analysis back and forth. And the Thevenin equivalent basically states that you can actually replace an entire network of circuitry with simply just one equivalent voltage and also in series with an equivalent resistance. And that actually simplifies our ability to work within the design process if other elements within the design are actually changing. So essentially what we do is we consider an entire linear circuit. And within that, right next to that linear circuit, we actually have maybe a load. And when I say load, that means any type of resistor, single resistor, or even resistive network that we're actually trying to supply energy to perform some type of work. Then we may not know exactly what value that we actually want to utilize for this load. So this whole linear circuit, this could be something up to like maybe 5 loops or some type of complex network that we really don't want to have to continue going through the analysis of. Basically, each time we want to actually change this value here. So what Thevenin's equivalent, based off its own theorem, actually says is that instead of going through and solving this entire network over and over and over and over and over again, we can just go ahead and take that entire network, solve it one time, and basically provide an equivalent voltage that exists between these 2 points, A and B, and also in series with a resistance that that load would have actually seen if we actually represent that linear circuit with one single resistance. And all we have to do is once we determine that Thevenin equivalent, we actually just take the voltage in series with the resistance and connect that back up to that resistive load, and we just go ahead and just solve with a single series loop, which is actually quite nice and quite easy considering that instead of actually doing systematic equations for multiple iterations, we can do it just once and take that equivalent circuit and just solve the system. So the process of actually gaining that Thevenin equivalent is to first actually disconnect that load. And once we've disconnected that load, we want to actually, in step 2, find the voltage that exists between these 2 points here, points A and B. And once we actually find that voltage, then we want to look at the equivalent resistance that would exist between those 2 points. So what we do is we turn off all of the sources within that linear circuit. So obviously, voltage source would go to 0 volts. We model that as a short. And if we had a current source, we take that current source, turn that off to 0 amps, and then we essentially model that as an open circuit. And then we just equate all of the resistance to those 2 points, A and B. So how does this actually work, and how do we actually practically develop a Thevenin equivalent? Well, we're going to look at 2 problems in order to exemplify this process. And so for the first one, it's kind of ridiculously simple. But start off with a simple process so I can actually prove that the process actually does work appropriately. Now, and you guys know I like to do proofs, but I'm going to need your help on this proof. So I expect you guys to be sitting there, cold beer in hand, ready to do a couple of calculations. Now, if we consider basically a very simple 2-loop circuit, 48 volts with a 12 ohm resistor, 4 ohms of resistance, 8 ohms as well as 5, we're actually going to consider the 5 ohm resistor as actually being our resistive load. And we want to find an equivalent resistance and also voltage about these 2 points. So what we're going to first do is disconnect this load. This 5 ohm resistor, we may not want to be 5 ohms. We may want it to be 10. We may want it to be 15. We may actually even want to put a capacitor there. We don't know. So what we're going to do is disconnect this guy, and then we're going to go through and find a voltage between these 2 points, and then actually find an equivalent resistance that 5 ohm resistor may actually see. So for the first step, we disconnect that load, and for the second step, we actually want to find a voltage that exists between these 2 points. Now, once we've actually disconnected that load with this circuit specifically, we have an 8 ohm resistor up here. And because that load is disconnected, no current can actually flow through that 8 ohm resistor. So by that notion, that 8 ohm resistor essentially doesn't even exist anymore. Because if no current flows through it, then we absolutely do not have any voltage that's going to be applied, because there's no work that's actually being done in order to get that current through that resistor. So what we actually have left as a resulting circuit to analyze is a simple series loop here. 48 volts in series with 12 ohms, and effectively in series with another, 12 ohms, and then effectively in series with another 4 ohm resistor here. And so between these 2 points, even though that resistor does exist, because no current flows through it, it doesn't actually impact the voltage at all. We simply get 48 by voltage division multiplied by 4 ohms over 4 plus 12, that gives us a cool 12 volts. So the voltage that exists in between these 2 points here, guys, is actually 12 volts. And one thing that's a shame about actually not having everybody in the lab is because I love actually showing how this works, because it usually throws people off that how could that voltage actually exist right here across that 4 ohm resistor if we still have an 8 ohm resistor right here. But in fact, actually what's going on is that 8 ohm resistor is acting more like a piece of wire, because, and just as a conductor, because there's nothing that's actually essentially going through it. So it's just simply allowing for a very simple series circuit. So with our Thevenin, or what we say as the resistance that's actually going to be seen by that load, then we consider basically the resistance that would be equated basically to these 2 points. So basically we short out, we turn off all our sources. In this case, we turn off a 48 volt source, and that actually effectively makes 12 ohms become in parallel with 4. And so 12 in parallel with 4 becomes 3, and then we add that on to the 8 ohm resistor. And once we add that on to the 8 ohm resistor, we get an equivalent resistance between these 2 points of simply being equal to 11 ohms. So the Thevenin equivalent for basically this small simple circuit is actually just going to be 12 volts in series with 11 ohms worth of resistance. Now, if we actually went through and solved for this circuit and solved for the voltage across that 5 ohm resistor, we would actually get 3.75 volts. With the Thevenin equivalent, if we take 12 volts and put that in series with our equivalence of 11 ohms as well, then this equivalent network, when we connect that back up to the 5 ohm resistor, by simple voltage division, will actually give us 3.75 volts. So you guys should actually go through, punch it in on your calculator, and make sure that that is consistent. That, sure enough, 12 volts in series with 11 and in series with 5 does give a voltage across that load that's actually the same. And that is the absolute point of the Thevenin equivalent, is that we replace an entire network that provides the same exact delivery of voltage to that load itself. And so from here, we actually can have a very, very nice design technique that allows us to solve maybe a complex network just once, so that we can actually continually work through and determine the appropriate value of the load that we actually want to connect up to this element. Now, Part of the reason why I want to make sure that I discuss this with you guys is because when we get into resistive capacitive, resistive inductive networks, I'm going to be saying the Thevenin resistance several times, and I want you guys to actually have a little bit of exposure to this so that you understand exactly what I'm talking about and know how to actually equate resistance by turning off basically the sources. So let's look at one problem that really exemplifies this process. But again, this is not going to be on the take-home test I'm going to be giving you guys. I want you to understand this process, and I will be giving you example problems that you guys can work through just in the event that you need some extra practice on this. So let's move the camera over this way. All right. All right, so this is 4.41. It's actually in your homework. There's actually a couple of extra problems that are within the homework that's on the eLearn site under course content. So within chapter 4, there's a few more. And if you want to actually work through these, it's fantastic practice for you guys. It actually helps you out with some of the other concepts that we've worked through already within chapter 4. But let's go through and take a look and see if we can develop a Thevenin equivalent for this entire network here. Now, step 1 has already been done. That load has already been disconnected. The author of the book wanted to go ahead and disconnect that load to actually simplify this process. So in this case, all we have to do is find the Thevenin equivalent between these 2 points here. So that means we have to find the voltage that exists between A and B. And then after that, we actually want to equate the resistance that would exist between A and B. So let's first take a look at the Thevenin equivalent. So here we can just go ahead and quickly perform source transformation. Let's just take 1 amp, so we take 6 ohms of resistor, we multiply those two together. By Ohm's law, we get 6 volts, and that puts that in series with 6 ohms, which causes basically a series equivalence here of 6 volts in series with 6 ohms, in series with 14 volts, in series with 14 ohms. And here we actually could see that would actually render 20 volts total, as well as 20 ohms worth of resistance. Now, an easy way of actually solving for this problem to find that Thevenin voltage is that if we consider the top node here, and basically that voltage would exist right here. We got 5 ohms that exists between those 2 points, and also a 3 amp source that exists between 2 points. And we know that voltage can exist between any 2 points within the circuit. So between A and B, where we see that we have the Thevenin voltage, that Thevenin voltage we can also repurpose, essentially, not repurpose, sorry, that's a bad phrase for that, just redraw it as this node right here. So V Thevenin actually exists between this point and ground. So by that notion, we can actually go through and easily just solve this with one equation, one unknown, just do a little KCL, just like we did back in chapter 2. So here, I'm going to allow current to move from the source to V Thevenin as I1 through those resistances. And then I2 is the 3 amp source, and then I3 is V Thevenin to ground divided by 5 ohms. So one equation, one unknown. So by KCL, you guys should know KCL and be able to recite that very, very verbatim. I1 is equal to I2 plus I3. So 20 volts minus V Thevenin over 20 ohms, that's the current that would actually flow through the left side of that circuit, is equal to 3 ohms plus V Thevenin minus 0, minus ground, over 5 ohms. And if we actually solve for this, one equation, one unknown, we actually get that V Thevenin is actually, in fact, equal to 8 volts. And that actually kind of makes sense because we have 20 volts that's being excited on the left-hand side, but we have a 3 amp source that's pointing downwards. And due to the resistances, it would actually suffice to say that negative 8 volts does, in fact, make sense. So, For the Thevenin resistance, if we go back to the first circuit here, before we did source transformation, for some reason I want to use that one instead of the source transform circuit. Doesn't matter. Here we just turn off 1 amp source, that gives us an open circuit. We turn off the 14 volt source, that gives us a short, and also the 3 amp source, that gives us another open circuit. We can easily equate the resistance between these 2 points here. And by doing that, and actually turning off all these sources and equating everything from the left to the right, then we actually can see that effectively we've caused 14 to become in series with 6, so that's 20. And so that thing becomes actually in parallel with 5 ohms, rendering a final resistance value or Thevenin value of 4 ohms of resistance. So the Thevenin equivalent is actually made up of the voltage that exists between those 2 points, which we found as actually being negative 8 volts, and then also the series resistance of 4 ohms. And so the final Thevenin equivalent that we actually have for the circuit is this simple series voltage and resistance right here. So, guys, if you have any questions, shoot me a message. There's going to be additional work that you guys will see on the course content under the Chapter 4 homework solutions. Take a look through those and make sure you understand and work through those. It will help you in the long run and also just help you for base knowledge. This won't be on the exam, but it was very imperative that I make sure that I cover that in this class and that you have this for reference material later on down the road. So, as always, stay safe and just stay cool, guys. All right.